We have another example on the board. Now, first, you're supposed to look at the polarity, right, of your diodes and the power supply. Please notice that this power supply is going to push the current in this direction, I total. This current is going to theoretically split into two currents, right? I'm going to call this I silicon, right? And this is going to be my current I germanium, okay? Means the current which goes through the silicon diode and the current which goes through the germanium diode, and current which goes through this resistor is going to be labeled I2, and current which goes through resistor R1 is my I1. Okay, so the power supply is pretty strong, 20 volts. So it means that I'm going to forward bias this diode and I'm going to forward bias this diode. Okay, so if the current, right, is going to flow in this loop, right, I'm forward biasing this diode. So it means that the voltage drop across this diode is equal to the transition voltage, right? So the voltage out 1, V out 1 or VO1 is equal V silicon, which is equal 0.7 volts. Okay, one more time, because the current is going to flow in this loop, right? You are going to forward bias this diode because the current is going to go in the same direction, like shows the arrowhead of my diode symbol. Okay, so the diode is forward biased, and because the diode is connected to the ground by the cathode and the anode is connected to V out, so I'm simply measuring the voltage across this diode, and this is my V out. V out is the voltage between this point and ground, so this is the voltage across this diode. That's why I said that V out 1 is equal to 0.7. So if I have 0.7 volts over here, so 0.7 is going to be divided into two voltages because this is series circuit. This resistor is in series with this diode. So 0.7 is going to be enough to forward bias also this diode. Why? Because the resistance over here is pretty small. 420 ohms is not very big resistance. So this voltage, 0.7 volts, is going to split into two voltages. Voltage across the resistor and voltage across the diode. Voltage across the diode is equal 0.3 volts because the transition voltage for germanium diode is 0.3 volts. And the output voltage 2 is taken from the diode, right? From across the diode. So it means that V out 2 or VO2 is equal V germanium, okay, which is equal 0.3 volts. Let me clarify myself one more time. Output voltage is the voltage between the ground and the output terminal, okay? So this is also the voltage across this diode, and because this diode is forward biased, okay, I'm supposed to say that the output voltage is equal to the transition voltage of the germanium diode. So we found output voltages. Next, in order to find the current which goes through this resistor, right? I mean the current which goes in this branch, what I'm supposed to do, I'm supposed to find the voltage across this resistor. We said that anytime current is entering the component, okay, because this current is going to go this way, I'm supposed to put positive sign. Anytime it's leaving, I'm supposed to write negative. So what I'm supposed to do next? If I want to find voltage across this resistor, I simply write that V out 1, right, is equal, V out 1 is equal to voltage source, right? Voltage source, positive voltage source, minus voltage across resistor R1. Why? Because I have negative sign. I'm going to this way. I'm going to the ground by using this branch. So I'm going to have voltage source minus voltage across resistor R1. If I want to find voltage across resistor R1, I'm supposed to simply move, right, negative VR1 to the left side and V out 1 to the right side. And I'm going to have V R1 is equal Vs minus V out 1, where Vs is equal 20 volts minus 0.7 volts is equal 19.3 volts. So this is voltage across resistor R1. So I can say VR1 is equal 19.3 volts. And if I want to find the current which goes through this resistor, I'm supposed to simply write that IR1 is equal to I1. Okay, this is equal VR1 over R1, where VR1 is equal 19.3 volts over R1, which is equal 1.2 kiloohms, and this is equal 16.08 milliamps. Okay, so this is the current which goes through resistor R1. This is my I1. Okay, so if I want to find the current which goes through the resistor R2, I'm going to simply write that V out 1 is equal, this time I'm going to write the KVL for this branch. So anytime current is entering the component, I'm supposed to write positive sign. Anytime it's leaving, I'm supposed to write negative, positive, negative. So V out 1 is equal positive VR2 plus VGE. So I have VR2 plus VGE. But I'm looking for VR2. In order to find VR2, I have to move my VGE to the left side. So I have VR2 is equal V out 1 minus VGE, where V out 1 is equal 0.7 volts minus 0.3 volts is equal 0.4 volts. Okay, so in order to find the current which goes through the resistor R2, I'm supposed to use Ohm's law. IR2 is equal I2, which is equal VR2 over R2, which is equal 0.4 volts over 420 ohms. So I2, we can say, is equal, of course, IR2, this is equal I germanium, and this is equal 952.38 microamps. Okay, so this is the current which will flow in this branch. Okay, will go through the resistor R2 and through the germanium diode. Next, the problem is asking me to find the current which will go through the silicon diode. How I can find it? You're supposed to realize that the total current is going to split. In other words, I1, right? I1 is also equal I total. So this current is going to split into two currents. So I can say that I1, which is also equal to I total, this is equal I silicon plus I2. Okay, this current is the sum of these two currents because it's going to split at this node. So in order to find ISI, right, I can write that I1 is equal ISI plus I2. In order to find SI, I'm supposed to move I2 to the other side of my equation, okay, and I'm going to have SI is equal I1 minus I2, where I1 we found is equal 16.08 milliamps minus I2, which is equal 952.38 microamps. Okay, so ISI is equal 15.12 milliamps. Okay, as you can see, we solved the problem.